Hi, today we're covering the Chapter 9 review questions from Discovering Design with Chemistry. So let's get right to it. We'll skip these first questions that are definitions that can easily be found in the book and start with question 2. A car is driving down the road with a velocity of 28.4 meters per second west. The magnitude of its momentum is 37,500 kilograms times meters per second west. What is its mass and what is the direction of its momentum? Okay, so let's go ahead and write out what we have here. So we are given a velocity, and that is 28.4 meters per second, and west. So in many of the most recent chapters, when we've talked about velocity and a lot of our other variables that are often vector quantities, we haven't treated them as vector quantities, and instead we've only used the magnitude. Starting in this chapter, we're going to start using the the vector variable more and treating it like a vector variable. And so let's go ahead and do something that we did in the earlier chapters and highlight and just give ourselves reminders that we might need to consider directionality in some of this. Okay, we have a west. We're going to define west as positive here and go from there. So we have velocity, then our momentum, which is abbreviated with the lowercase p, equals 37,500. I'm not going to put east or west here because it's positive, and so we'll just keep it as a positive number. Okay. So with this, we are going to use our equation 9.1 to determine what the mass is. And you remember that equation is P equals mass times velocity. And so we're going to be solving for mass. So we'll be dividing the momentum by the velocity to get mass. And so then that's going to be 37,500 kilograms times meters per second divided by 28.4 meters per second. And that is going to give us 1,320, and the units, the meters per second, are going to cancel, and so we're left for kilograms. Okay, and so with this, the car's mass is 1,320 kilograms. There are two parts to this question. What is its mass and what is the direction of the momentum? And in this case, the direction of the momentum is going to be the same as the velocity. And funny enough, the question actually told us the direction of its momentum. So the car's mass is 1,320 kilograms, and the direction of momentum is west. Okay, for question 3, two objects are moving with the same velocity. The first has 3 times as much mass as the second. Compare their momenta, which is the plural of momentum. Be as detailed as possible. So in this case, if the first has 3 times as much mass and their velocities are the same, well, because you have P equals mass times velocity, if you multiply this mass times 3, you're going to be multiplying the momentum times 3. So the first will have 3 times the momentum as the second. For question 4, 2 identical objects slam into 2 different obstacles with the same velocity. The first hits a hard wall. The second hits a soft cushion. They both end up stopping. Compare the impulses the objects experience. Compare the time over which they experience those impulses and compare the forces that they experience. So let's just have a reminder about our impulse equations. These are equations 9.4 and 9.5. So for 9.4, our delta P, which is our impulse, equals force times the change in time. And then we also know that delta P, our impulse, is the final momentum minus the initial momentum. Okay, so the impulse they experience will be the same. The second will experience it over a longer time period, and the force it experiences is smaller. Okay, so impulse is that change in momentum. They each have the same mass and the same velocity, and so they have the same momentum. They each come to a stop, so they have the same change in momentum. Because the second one hits a cushion, though, the cushion is going to deform, and that's going to increase the time over which the object stops. And so since impulse is the force times the time, an increased time would lead to a decreased force. So that is the answer, that the impulse is the same, and the second experiences it over a longer time period, and the force it experiences is smaller. So those are the answers to the 3 questions, along with the explanation of how we get those answers. For question 5, a 59.4 gram tennis ball is traveling at a speed of 47.0 meters per second, and it's hit by a racket. It leaves the racket with a speed of 51.7 meters per second, but it is now traveling in the opposite direction. If the racket exerted a force of 617 newtons, how long was it in contact with the ball? So I'm going to start out here. Let's just start highlighting and giving something some signs, because there are a couple directions that are definitely happening in this question. So we have a speed, and we're given the word speed and not velocity, but because we've just read that something's going to go in the opposite direction, we're just going to go ahead and going to assign this a direction and call it velocity. Okay, so this speed is really velocity, and let's just call this forward, the initial direction. Okay, and we're going to assign that as positive. Okay, it leaves the racket with a speed of 51.7 meters per second. Okay, so, and is now traveling in the opposite direction. So the initial speed, it's going this way, then the racket hits it, and it's now going the opposite direction. So we have another speed here, and this is going to be velocity backwards. I'm going to call it V back, and it's going to be negative. Okay, if the racket exerted a force of 617 newtons. Okay, well, force is also a vector quantity. So let's highlight that, and let's think about what this force needs to be as far as positive or negative. So it's the racket exerting that force. So ball hits the racket, racket exerts force the opposite direction. And so we're talking about that backwards direction. And so this force here is going to be negative. So let's now write out all of our known variables with the signs that we have assigned, okay? So our mass is 59.4 grams. And of course, we're going to change that to kilograms. 0.0594 kilograms. We have velocity, we'll call it forward. I'm just going to say 4, and that equals 47.0 meters per second. Then we have a velocity backwards, and that's going to be a negative 51.7 meters per second. Okay. We also have our force, and it's going to be a negative 617 newtons. Okay. And what we need to find out is a delta T. What is our time? So where do we begin here? Well, we do have one equation that includes force and time that we've learned from this chapter, and that's equation 9.4, our change in momentum given force. And so that equation is delta P equals force times the change in time, right? Now, we were given force. We don't know delta P yet. So we're going to need to find that out. I'm going to do that over here. Our delta P, we know, our impulse is our final momentum minus our initial momentum. So let's put these things together. So we're going to have our mass of our ball times velocity. I'm going to call it F. We called it 4 up here. I'm just going to put F here. And so that is our, actually, wrong way. Backwards, our backwards velocity, right? So the final is our velocity going back minus our initial, so it's this mass times our velocity going forward. I don't really like this F here because F makes me think final, and that's why I did that here, but we'll just go with it. We'll keep it as F4. So let's plug in our numbers here. Our mass is 0.0594 kilograms times our velocity going backwards is going to be negative 51.7 meters per second. And we subtract our mass again. Times our velocity going forward, 47.0 meters per second. And so with that, we'll get negative 3.07 kilograms times meters per second, which is our momentum units, minus 2.79 kilograms times meters per second, and ultimately get negative 5.86 kilograms times meters per second. Okay, so this is the change in momentum or impulse that is going to get plugged into here. So now I really like to move things around and solve for what I'm going to be looking for before I plug in the numbers. So let's do that. We're going to be solving for delta T. So this is going to be delta P divided by the force to get our time. Okay, so now we can just plug these in. We have negative 5.86 kilograms times meters per second, divided by our force, negative 617. Let's go ahead and change this newtons to a units that we can more easily divide or cancel out units, okay? So kilograms times meters per second squared, right? And so everything is going to cancel except for this last seconds, which will then be up in the numerator. So negative 5.86 divided by negative 617, we're going to get 0.00950, going to 3 significant figures, seconds. Okay, and so our final answer is that the racket is in contact for 0.00950 seconds. And that is the only question that we're answering for that. For question 6, two objects collide while they are in free fall. Will momentum be conserved? And the answer is no, it will not be conserved. And that is because momentum is only conserved when the net force is 0. Well, in free fall, the only force is gravity and it's pulling down. So that net force is a negative, if you consider down negative force, and it is not 0 when the objects are in free fall. For question 7, two objects collide while they are falling at their terminal velocities. Will momentum be conserved? And the answer there is yes, it will be conserved, because at terminal velocity, the acceleration is 0. That means there's no net force. It happens because air resistance is equal to the force of gravity, and so the net force is 0. And so that's what is required for momentum to be conserved, and so it will be conserved in that instance. For question 8, a 15.9 kilogram sniper rifle has a recoil velocity of 2.25 meters per second. If it fires 42.0 gram bullets, how fast do those bullets leave the rifle? Okay. So we have velocity here, and specifically this recoil velocity, which is the velocity that the gun is moving backwards when it fires that bullet forwards. So I am always going to call this recoil velocity negative. If you choose to use it positive here, that's fine, as long as you give the bullets the opposite direction, and you'll get the same answer. But for this example, I'm gonna call it negative, and it's gonna fire 42 gram bullets. And how fast do those bullets leave the rifle? So this question is actually just asking speed. So you could technically not give the direction, since it doesn't say velocity, it just says how fast. We'll talk about the direction though. Okay, so what are we given? We have the mass of the rifle, which I'm going to call MR, and that's going to be 15.9 kilograms. We have the mass of the bullets, I'm going to call that MB, and that's 42.0 grams, which we're going to need to convert this to kilograms, 0.0420. Keep that 3 significant figures, kilograms. We have the velocity of the rifle, which we've defined as negative. So it's going to be negative 2.25 meters per second. And that's all we're given. What we need to find out is what the velocity of the bullets are, right? So let's use this equation, P before equals P after. So our momentum before and our momentum after. Okay, so our momentum before is 0 because there is no velocity. Before this rifle is fired, nothing is moving. Our momentum after consists of 2 different momentums. We have the momentum of the bullet, and we have the momentum of the rifle. Okay, or you could say PB plus PR. So now let's break that down. So our momentum of our bullet is of course going to be our mass of our bullet times our velocity of our bullet. And our momentum of our rifle is going to be our mass of our rifle times the velocity of our rifle. So I'm going to have a negative mass of the bullet times the velocity of the bullet. I just moved this over here. Equals mass of a rifle times the velocity of the rifle. I'm going to divide all of that times negative mass of the bullet. And that will leave me with the velocity of the bullet. So now we can plug in all those numbers. We have 15.9 kilograms times negative 2.25 meters per second. Divide that by negative 0.0420 kilograms, which is my mass of my bullet. And we're going to get, kilograms will cancel. We're going to be left with meters per second. It's going to be 852 meters per second is the velocity of the bullet. So the velocity of the bullet is 852 meters per second in the direction the gun points. You can't really say away from the gun because that could be any direction away from the gun, but in the direction the gun points. And of course, this question didn't actually ask us for velocity, so you could have just said the speed of the bullet is 852 meters per second. For question 9, a pistol fires 195-gram bullets with a muzzle velocity of 319 meters per second. If its recoil velocity is 5.3 meters per second, what is the mass of the pistol? So we have this muzzle velocity, and that's not to be confused with recoil velocity. The muzzle velocity is actually giving us the speed at which the bullets are flying out of the gun, and so this is going to be positive. Okay, then we have the recoil velocity, and that's going to be negative. Let's now write out what we have here. We have the mass of our bullets equals 1.95 grams, which is equal to 0.00195 kilograms. We need to know the mass of the pistol. Our velocity of our bullets is 319 meters per second, and a velocity of our pistol is 5.3 meters per second. And so we're going to use the same kind of equation as before. Our P before equals our momentum after. Before is going to be 0 because the gun is not moving, the bullets are not moving. And when that velocity is 0, 0 times the mass is going to be 0. And our P after, we're going to take our, once again, our mass of our bullets times our velocity of our bullets plus our mass of our pistol times the velocity of the pistol. Okay, this time we are solving for the mass of the pistol, and so let's move everything around accordingly. So I'm going to move this over, so we have negative mass of the pistol times velocity of the pistol equals mass of the bullet times velocity of the bullet, and we'll divide both sides by a negative velocity of the pistol to get mass of the pistol. So plugging in all those numbers, 0.00195 kilograms mass of the bullet times our velocity of our bullet, 319 meters per second, dividing all of that by a negative velocity of our pistol. And I didn't put this sign here like I said we were going to, but that's going to be a negative, right? So this is recoil velocity, it's negative. So negative, negative, right? Negative, negative, which is going to be positive, right? 5.3 meters per second. So we can just cancel out those negatives. And so when we multiply all that out, 0.12 kilograms. So our final answer is the mass of the pistol is 0.12 kilograms. It's a little pistol. Okay. For question 10, a 87.2 kilogram man in roller skates is standing still. Someone throws him a 566 gram basketball at 13.3 meters per second. When he catches it, ignoring friction, what will be his velocity? And is this an elastic or inelastic collision? Okay, so we have a velocity here. It's not labeled velocity, but, and let's just go ahead and assign this a positive value. Okay. We're also given a velocity of the man, and that's that he's standing still, right? So the velocity there is 0. And then of course we're going to be asked what his velocity is, so we're going to need to give a direction there. So write out what we have. We have our mass of our man, so I'm going to say mm, and that is 87.2 kilograms. We have this mass of the ball, and that's 566 grams, which is going to be equal to 0.566 kilograms. We have an initial velocity, which is 0. And this is the initial velocity of the man too, right? And then we have velocity of this ball, which is 13.3 meters per second. So let's just use this old friendly equation again. P before, momentum before, equals momentum after. We are conserving momentum. Okay. And breaking this down, it's not going to be quite as simple as these, because our momentum before, there is actually a momentum that is happening before, and that's the momentum of this basketball. The man is standing still, so his velocity is 0, his momentum is 0, but the basketball has a momentum, and our after momentum is going to be a combination of the man and the basketball together once he has caught that ball. Okay, so our P before, from let's just write out everything that would be included here, right? So we have these two separate momentums of the man and the ball. So mass of the man times velocity of the man plus our mass of our ball times the velocity of our ball equals, our after is going to be the mass of these two things together. The man is now holding the ball, so this mass is the combination of both of them. So mass of man plus ball times our velocity of our man plus ball. Okay? We're solving for this one. So let's just go ahead and, since we're solving for that, we're going to be dividing all of this by the mass of the man plus ball to get this velocity of the man plus ball. So mass of our man times the velocity of our man. We're going to do a little shortcut here. This velocity of our man is 0. The mass of our man doesn't matter. So this in total is 0. Plus our mass of our ball is 0.566 kilograms times the velocity of our ball, 13.3 meters per second, and dividing this by the mass of the man plus the ball. So we're going to be adding 87.2 kilograms plus 0.566 kilograms. Now, remember here are rules for addition and significant figures, right? So we're going to the least precise digits. So that's only to the 10th place. And so we're actually going to be adding 87.2 times 0.6. Okay? And so we'll get 87.8 there that we are dividing this by. Okay? So when we do all that, then we will get 0.0857 meters per second. 3 significant figures here. So now we have what the man's velocity is going to be. And there are 2 parts, though, to this question. We're asking what is velocity and is this an elastic or inelastic collision? So for elasticity, we need to be comparing the kinetic energy. Is the kinetic energy before the collision the same as it is after the collision? So let's do that. We have kinetic energy before, okay, and just as a reminder, kinetic energy equals 1/2 mass times velocity squared. Now, before, just like with the momentum, we have 2 parts, right? We have the kinetic energy of the man and the kinetic energy of the ball. Now, the kinetic energy of the man is going to be 0, okay, because his velocity is 0, and so that's going to make his energy 0. So we can just say 0 for the man, but let's figure out the kinetic energy of the ball. So it's our mass, 0.566 kilograms, times our velocity, 13.3 meters per second squared. And with that, we get 50.1 joules. Now let's compare this to the kinetic energy after. So after, just like with the momentum, we have the man and the ball joined together. And so we're going to be using that mass of the 2 together, which we said was 87.8. And our velocity after is what we just figured out, 0.0857 meters per second squared. And we get 0.3 322 joules. So to determine whether this collision is elastic, we're comparing these two kinetic energies. Are they the same? And absolutely not. They're not even close, right? So this is therefore going to be an inelastic collision. So our final answer is that the man will roll, because he's on roller skates, the direction the ball was thrown, at 0.0857 meters per second, and the collision is inelastic. Question 11. Two balls are rolling towards one another on a level surface. The first has a mass of 1.2 kilograms and a speed of 3.7 meters per second. The second has a mass of 3.1 kilograms and is rolling at 1.2 meters per second. They collide head on. After the collision, the first one is rolling with a speed of 3.4 meters per second in the opposite direction compared to how it was rolling initially. What is the velocity of the second ball, and is this an elastic or inelastic collision? So let's go through and assign signs to our vector quantities. We have this first ball that has a speed of 3.7 meters per second. Since it's the first ball, we're just going to go ahead and give it a positive value. The second ball is rolling at 1.2 meters per second and is colliding head on with the first ball, which means that it has a velocity that is exactly that is opposite of what the first ball is. And so we're going to give it a negative value. After the collision, the first one is rolling with a speed of 3.4 meters per second, and it's in the opposite direction of how it was rolling initially. So it was initially positive, and now it's going to be negative. And then we need to know what the velocity is of the second ball. So we have velocity here, and then is it elastic or inelastic? This question is asking a lot of us in terms of calculations, and they've barely given us enough room. So it's going to know that and conserve space as we are doing the problem. Okay, so what we're given, we have M1. I'm going to call anything related to the first ball 1 and the second ball 2. So our first mass is 1.2 kilograms. Our mass of our second ball is 3.1 kilograms. The velocity of our first ball is 3.7 meters per second, and that's positive. The velocity of our second ball is a negative 1.2 meters per second. Our velocity of our first ball after the collision is a negative 3.4 meters per second, and we don't know what our velocity to after is. Okay, so we're going to use this same equation that we've been using several times. Our momentum before equals our momentum after. We are conserving that momentum. So before here we have two balls, after we're going to have two balls, and they're just going at different velocities. So before we'll have M1 times V1 plus M2 times V2 equals M1 for after. The mass stays the same, of course, times the V1 after plus M2 times the V2 after. And this is what we're solving for, so let's go ahead and shuffle things around here. So we have still the M1 times V1 plus M2 times v2. We're just going to subtract this m1 times v1 after, and we'll divide all of this by the mass of the second ball. And that will give us our velocity of the second ball after the collision. So let's plug everything in here. We have 1.2 kilograms times 3.7 meters per second plus our second ball is 3.1 kilograms times a negative 1.2 meters per second. Now we're subtracting our first ball, 1.2 kilograms times a negative 3.4 meters per second. That's its afterwards velocity. And dividing all of this by the mass of the second ball, which is 3.1 kilograms. So whenever I have multiplication and addition all together, I'm going to do the multiplication first so that I am making sure that I'm following our rules for our significant figures. So our 1.2 kilograms times 3.7 meters per second is 4.4 kilograms times meters per second. Then this here is going to give us, it's going to be negative because of the one negative sign. So minus 3.7 kilograms times meters per second. I'm paying attention this time, and I have two negative signs, so this is going to be a positive 4.1 kilograms times meters per second, and all of this is divided by 3.1 kilograms. And so that gives us 4.8 kilograms times meters per second divided by 3.1 kilograms and 1.5 meters per second as our ultimate velocity. And remember that this is going to tell us our direction too, and it's going to be going in the same as the initial direction of the first ball, or you could say the opposite direction of what this second ball was originally rolling. But that's only half the question. We also needed to find out if this is elastic or inelastic collision. So for elasticity, we are comparing the kinetic energy before and after the collision. Now, as a reminder, kinetic energy equals 1/2 mass times velocity squared. Now, we have two balls here, so the kinetic energy is going to be the sum of the energy of those two balls, both before and after the collision, okay? So our KE, I'm going to call it B for before, equals, we have 1/2 our mass of our first ball times our velocity and then we're adding the kinetic energy of the second ball, so 1/2 the mass of the second ball times the velocity. And with that, we will get 10.4 joules. So now for our after, we have 1/2 our mass of the first ball times the velocity of the second ball after this collision squared plus 1/2 mass of the second ball and times this velocity that we just got squared. And that comes out to also 10.4 joules. So this collision is in fact elastic because the kinetic energy is the same before and after the collision. Our final answer here is the second ball's velocity is 1.5 meters per second. We're going to say opposite of its original direction. And the collision is elastic. And that answers both of these questions. What is the velocity of the second ball, and is this an elastic or inelastic collision? For question 12, an astronaut is working on the outside of the space station. A small asteroid hits him, knocking him off the space station. To his horror, he sees that the asteroid also broke the line holding him to the space station, so he is drifting away from it at 1.5 meters per second. Because he knows physics, he calmly spins around so that his back is to the station and throws his 14-kilogram tool directly in front of him at 25.0 meters per second. If he and his space suit have a mass of 195 kilograms, what happens? What will be his velocity? This is kind of a fun question, but it's a little bit complex. So, looking at our vector quantities, he's drifting away from the space station at 1.5 meters per second. And because the space station is where he really wants to be, we're going to call this direction away from the space station negative. Okay, then he throws this tool, and he throws it at a speed of 25 meters per second. But it's not opposite of the way he's facing, because he has spinned, it's the same way he's facing, but it's not opposite of the space station. He has spun around, so his back is to the space station, and this tool is in front of him. Okay, so he's drifting this way, but he also turns this way and throws the tool the same way as he is drifting. So this is going to be a negative value also. And then of course, we're asked what his velocity is. So let's now write out what we know. We know this mass of this astronaut, 195 kilograms. We know the mass of the tool is 14 kilograms. We have this velocity, which is negative 1.5 meters per second. And we have a velocity of a tool, which is negative 25.0 meters per second. Let's think about what is happening. We have this same equation that we have used so many times today. The P before, our momentum before, equals our momentum after. So before, there's this astronaut, and he's drifting away. After, this tool that was in his hand that he was using to work on the space station, he throws it away from him. So before, he actually is in possession of this tool, and the mass that we use for our momentum needs to include the tool as well. This velocity also includes the tool, because he's holding this tool while he starts drifting away at negative 1.5 meters per second. Then after he throws the tool, and now we have two separate things. We have the astronaut who has some sort of velocity after he throws the tool, and the tool that has its own velocity. And the astronaut now doesn't have the mass of the tool with him. So let's put this together. So before, it's going to be the mass of the astronaut plus that tool he's holding times the velocity of the astronaut and the tool that he's holding. And then after, we're going to have the mass of the astronaut times the velocity of that astronaut plus the mass of the tool times the velocity of the tool. And we're going to be solving for the velocity of the astronaut. That's what we need to determine. So let's rewrite this. We're going to subtract this mass of the tool times the velocity of the tool, and then divide everything by the mass of the astronaut to get the velocity of the astronaut. And now we can plug in. So I'm just going to do this in my head. The mass of the astronaut plus his tool is going to be 209 kilograms times negative 1.5 meters per second, the velocity of both of them together, minus the mass of the tool, 14 kilograms, times negative 25.0 meters per second, and dividing all of that by the mass of the astronaut, 195 kilograms. So doing these multiplication parts first, I'm going to get 310 kilograms meters per second. And this is a negative 310 because I was multiplying 209 times negative 1.5. And then here I'm going to be adding, because I have two negatives here, minus and minus. And that's just going to be 350 kilograms meters per second. And then dividing all that by 195 kilograms. So this comes out to 40 kilograms meters per second divided by 195 kilograms, and that gives us 0.2 meters per second. Now, how did I end up with just one significant figure here? Okay, so here on the addition, only two figures could be significant because in each of these, there was only two significant figures as my lowest one, okay? And so it was only significant to the tens place. So that means here, once I complete this addition, this is only significant to the tens place, okay? And so since I only have one significant figure up here, my answer has to be in one significant figure. Okay, and so then my final answer here is that the astronaut will go back toward the space station. Notice this velocity is positive. At 0.2 meters per second. So there's two questions here. It asks what happens and what will be his velocity, and we're answering all of that all together. He's going back towards the space station at 0.2 meters per second. Just answering the velocity tells us what happens. For question 13, in the Newton's cradle pictured on the right, two balls are lifted to a specific height. They are released and allowed to crash into the other balls. What will happen after the collision? Describe both the number of balls that will move and the maximum height they will reach. And ignore air resistance. Okay, so if two balls are lifted and dropped, that means that two balls on the other side will, with the same speed, they're going to rise to the same height before falling back down. And that is because momentum and energy must be conserved, and that's the only way that that can happen. For question 14, a man is shopping with his daughter. She pushes the grocery cart so it is rolling on its own. As the cart passes him, the man places a heavy item in the cart. Assuming he places it there with essentially no velocity, what will happen to the speed of the cart and why? So what will happen is that the cart will slow down because the increased mass of this new object that he's placed in the cart is going to force the velocity to decrease in order to keep the momentum the same. So momentum is mass times velocity. So if you increase the mass, the velocity is going to change for conservation of momentum so that the momentum is the same before and after. Question 15. A gun is used to shoot a 5.66 gram bullet into a 678 gram ballistic pendulum. The pendulum rises to a height of 0.15 meters. At what speed did the bullet leave the gun? Okay, so we don't have any vector quantities here. Speed, could be translated to velocity, but it just says speed here, so that's all we need to answer. And so let's go ahead and write out what we have. We have a mass of a bullet, which is 5.66 grams, which is going to be the same as 0.00566 kilograms. We have this pendulum, so the mass of the pendulum equals 678 grams, which is going to be equal to 0.678 kilograms. And we have this height that the pendulum achieves, which is 0.15 meters. And we need to know what the velocity of the bullet is. So we can use height to determine the potential energy, which will tell us what the total energy of this entire sequence of events is. And remember, the total energy remains the same at any part of this sequence of events. So why that works is, remember that total energy equals kinetic energy plus potential energy. Okay, and at this height, we could say that this is the final, right? The final part of the energy here. And once this pendulum has reached this maximum height, there is no more movement going on. And so this kinetic energy is zero. There's no velocity happening at that point. And all you're left with is potential energy. So total energy equals the potential energy. So let's determine what this potential energy is. Our potential energy equation, as a reminder, is mass times gravity times height. And so in this mass, this is after the bullet has hit the pendulum. So it's actually a combined mass of the bullet and the pendulum. And so mass of the bullet plus the pendulum is 0.00566 kilograms plus 0.678 kilograms. And remember, we can only go to the least precise digit. Okay, and so this is going to be like we are adding 0.006 to this. And so we'll get 0.005 0.684 kilograms as our mass of the bullet plus the pendulum. Let's plug that in there. Times 9.81 meters per second squared times our height of 0.15 meters. And so that is going to give us a total of 1.0 joules, to two significant figures. So that is our total energy in our system. So now that we have the total energy, we can use that to determine what the kinetic energy is at the time that the bullet hits the pendulum. So before the pendulum has reached all the way to its final height, what is the kinetic energy of the bullet and the pendulum? We're going to call this initial, even though it's not like the moment the bullet was fired. It's kind of like a midpoint here. So again, the total energy is the kinetic energy plus the potential energy, but now we know the total energy. And that's going to be 1.0 joules. Our kinetic energy is going to be what the energy is of the bullet moving inside that pendulum with the pendulum. And so we have 1/2 times our mass, and that's going to be the mass of the bullet and the pendulum again, times our velocity squared, which we don't know at this point. Now, plus the potential energy, but the potential energy is going to be 0. And that's because that pendulum has no chance of moving any lower. It's already at its minimum height at the moment that the bullet hits it. So there is no potential energy stored in the pendulum and bullet at that point. So now we can divide by 1/2 times 0.684 kilograms. And then we're going to take the square root of all of that to get the velocity. And this is the velocity of the bullet plus the pendulum, okay? And we'll get 1.7 meters per second. And that is the velocity of those two things together. But the question isn't asking us that. It's asking what speed did the bullet leave the gun. But now we're at a point where we can use our conservation of momentum to determine that speed. So let's pull out this equation again. We have P before. Okay, and our before is going to be our mass of a bullet times the velocity of the bullet. And then when it hits that pendulum, now it has momentum with the pendulum. And so that's going to be the mass of the bullet plus the pendulum times the velocity of the bullet plus the pendulum. Now, what we're determining here is the velocity of this bullet. And so to do that, we'll be dividing by all of this by the mass of the bullet. So our mass of the bullet plus the pendulum, 0.684 kilograms, times our velocity of the bullet and the pendulum, what we just figured out, 1.7 meters per second, divided by the mass of the bullet, 0.00566 kilograms. Our kilograms will cancel. We'll get 210 meters per second. Our final answer is the bullet left the gun at 210 meters per second. Question 16. Use angular momentum to explain why it is easier to keep a bicycle upright when it is rolling compared to when it is standing still. So the answer there is that when this bicycle is moving, the wheels have angular momentum since they are moving in a circle. And so to change that angular momentum requires a torque. And that adds to the torque needed that an unmoving bicycle would need to tip over. So there's more torque required when a bicycle is moving to tip it than what is required when the bicycle is standing still. Question 17. A charged particle is traveling in a circle of radius 15.0 centimeters with speed of 156 meters per second. The magnetic field that is holding it is changed so that the circle decreases to a radius of 7.5 centimeters. If the magnetic field exerted no torque on the particle, what is its new speed? So now here on this problem, there's a speed, but we don't have any direction associated with it. This is going to be a magnitude and not a vector quantity. So we're not going to do any highlighting here and reminders of direction that we need to put in here. So let's write out what we have. We have the radius of this particle, that is the initial radius, and that's 15.0 centimeters. We have the radius of this particle at the end, and that's going to be 7.5 centimeters. Now you can, if your first instinct is to go ahead and change these to meters, go on right ahead. But in this particular problem, we don't have to do that. So I'm not going to. And you'll see why in a second. So then the velocity here equals 156 meters per second. We're going to be using here is equation 9.8 that tells us that when the sum of torques is 0, L before equals L after. And L is the magnitude of the angular momentum. Okay, so this angular momentum is the same before as it is after, as long as there is no sum of torques that is other than 0. So that L is defined in equation 9.7 as mass times velocity times radius. Okay, so our mass we were not given, but our initial velocity, our initial radius there, and then our after is going to be mass times our final velocity and our final radius. Okay, and so this velocity that we were given here is an initial velocity. Okay, mass is on both sides of this equation, so it cancels out, and so we're just left with this. We're solving for our final velocity, so we can divide our initial velocity times radius by the final radius to get that. So now plugging everything in, our initial velocity, 156 meters per second, times our initial radius, 15.0 centimeters, divided by our final radius, which is 7.5 centimeters, and this is why I left it at centimeters, because I knew that I was going to do this and they just cancel. And so the units there don't really matter because we're going to end up with meters per second no matter what. And so when we calculate all of that out, we get 310 meters per second with two significant figures as our speed. New speed is 310 meters per second. Question 18. A 22.0 kilogram object is traveling in a circle with a radius of 5.12 meters. Suddenly, the radius decreases to 3.56 meters, but the speed is unchanged. Assuming no torques were exerted, what happened to make the change? And be as detailed as possible. So we're given a mass. We have a radius. And that is an initial radius. And then we have a final radius. Okay, and so what it's saying is that in this equation that we used before, the radius changed, the velocity remained constant. So if the velocity is constant, it cancels out on both sides. And so how can the radius change? The only way it can change is that the mass changes. Okay, and so let's figure out exactly how the mass changed. So that means that we do have a mass initial and a mass final. And then this was our initial. And we need to figure out how exactly the mass changed. We're going to be solving for this final mass. So we'll divide the initial mass and radius by the final radius to get that. So we have 22.0 kilograms times 5.12 meters, and divide that by 3.56 meters. Meters will cancel, and our final mass is 31.6 kilograms. So what happened to make this change is that the mass increased to 31.6 kilograms. So then with this question, it says be as detailed as possible. This doesn't seem like a detailed answer, but it's more detailed than saying the mass changed. And so that's what the question is going after, is that you actually give the actual amount that the mass changed. That is it for these Chapter 9 review questions. And if you have any questions about this, just feel free to post them in the comments.